Thanks. Yep. Okay, so there's 52 people. Okay, I guess that's the usual. Okay, so let's start. I'll plan to just finish the lectures in one sitting. If I can, so we can go early, but at least so we can finish all of the slides. So of course we are starting a little later than I had anticipated. So anyway, we stopped with this slide, last Monday. This summarizes the transport of oligopeptide via peptide-1. So in today's lecture and onwards, we are going to be discussing lipid absorption, and then mineral, water, ion absorption, vitamins. We will discuss motility, and we will also introduce the gut microbiota. So we begin. We started with fat digestion, and in the very first few slides, I mentioned the fact that digesting and absorbing fats, especially digesting fats, is a lot more complicated than carbohydrate and protein digestion because of its biophysical property, biochemical property as a hydrophobic substrate. And we know that we need an aqueous solution to digest our nutrients. So what is happening in the stomach to the lipids that you eat? So in the stomach, the fats actually separate out. So just like for those of you who cook, who sometimes mix aqueous solutions with vegetable oil, for example, you will know, and for those of you who work in labs, that lipids would float on top of an aqueous solution, right? So it's the same thing in your stomach, although it's not, the demarcation line is really not that sharp, because the stomach is also actually contracting. So there, relative to the volume, there's a small surface area of these large fatty globules. And these large fatty globules are eventually emptied into the duodenum. And in the small intestine, where the duodenum is the most proximal region, the bile in the small intestine from the liver, the bile from the liver that released into the small intestine actually emulsifies the fat globules. So now the surface area to volume ratio is markedly increased, and now the pancreatic lipase can do its work more efficiently. So this is your fat globules, these are your bile acids, your phospholipids, and so now we have them emulsified, and we have these bile salts surrounding the emulsions, because the bile salts essentially, which act as a detergent to emulsify the fat globules. And it is on these emulsions that the lipase, actually pancreatic lipase, will work to digest them, so that we have fatty acids being released as digestion products. So what are the enzymes that are actually needed for lipid digestion? So there's actually, it's called glycerol ester hydrolase. And the common name actually is pancreatic lipase, although different books mention, different books mention these two different names. And it is actually secreted in the active form. And it needs colipase for the hydrolysis of lipids in the presence of bile. What's going on then? What is colipase? So it is secreted from the pancreas into the intestinal lumen as inactive procolipase, and then it is activated in the intestinal lumen. It's required by pancreatic lipase. And so what does actually colipase do, and how does lipase and colipase interact, and what happens to lipid digestion? Okay, so this is important. And then also we have cholesterol esterase as part of the list of enzymes for lipid digestion. And we have phospholipase, which digests your phospholipids. Okay, and this one, as the name implies, digests cholesterol esters. So here you see the x-axis is time, the y-axis is fatty acids released. So these are digestion products from pancreatic lipase. And what's going on in this graph? So scenario number 1 is this dashed line here. If you go to the original, actually to the book from which I got this from, you actually will find that there is a different slope, and I corrected the book, and so this is the correct. So the slope here is actually less than the slope here. So what's actually going on? So this is your fat droplet, right? This is droplet before emulsification. So your pancreatic lipases are nibbling on the surface. And as I mentioned, the rate of fatty acids released are going to be slow because there's only so many enzymes that can bind to the surface area of these fat globules. So it's working, but not efficiently. So what does colipase do? So when bile acids are released and emulsifies the fat globule, then now you have an increased surface area. The problem when bile actually binds to the surface of these fat globules, which result in emulsifying them into droplets, then the bile acids not only make smaller droplets because it's emulsifying the globules into droplets, but it's also kicking out the lipase. So in this scenario, actually the lipase has been kicked out. And the bile acids actually displaces the pancreatic lipase. So digestion stops as shown by this fatty acid released here. Then what colipase does is to actually grab the pancreatic lipase, displace the bile acids on the surface of this emulsion, and then bring the lipase back onto the surface. When
Professor,
the colipase brings the lipase back into the surface of the emulsion, now there's a much greater surface area to volume ratio. And so now what happens is there's a dramatic increase in the rate of lipid digestion by pancreatic lipase with the help of colipase. And so the rate of fatty acid released, because of now the pancreatic lipases is acting on a large number of emulsions, is actually dramatically increased.
Professor.
Okay, so this is really the role of colipase. So now we have the fat digestion products. We have phospholipids, we have free fatty acids, we have 2 monoglycerides, we have free cholesterol. Now they are existing in an aqueous medium, but entropy works against them. They don't know whether they should stay there or not. And so, so this is then a continuation of that slide I showed in the previous slide. And so now after lipase and colipase digest away the fatty acids shown here, and this is 2 monoglycerides. So if you put these together, these are triglycerides. They compose virtually almost all of the lipids that we eat, right? So the lipase releases 2 free fatty acids and 2 monoglycerides. And then these monoglycerides and free fatty acids are then incorporated into micelles, as depicted here, and as I depicted previously in last Monday's lecture.
Dr. Ferraris?
So now these are here.
Dr. Ferraris?
And they are surrounded by bile acids.
Professor?
And so therefore, the aqueous medium is here, the aqueous medium is here, but the lipids, the hydrophobic elements of our nutrition is now actually in the middle of this micelle. So why are micelles very important? Yes. Good point. Okay, thank you for that reminder. Okay, so yes, yeah, I can't see very well the chat. Okay, so there's a request. Okay, my apologies for that. Okay, so now you have these micelles, and I've shown you the micelles last Monday. They basically incorporate these fat digestion products. So what do they do, and why are micelles not only serve as a holding station of these hydrophobic digestion products of pancreatic lipase and colipase? Well, the micelles actually help in absorption. So what's going on when, so this is a cross section, a very, very, I would say, high magnification of an intestinal cell. So this is your lipid bilayer. This is brush border membrane, is the membrane of your intestinal cell. So this is your cytosol. This is the aqueous medium here. And these are the products of lipid digestion incorporated now into micelles. So what? So what? And what is this unstirred layer that's overlying the surface of all of these intestinal cells? So the intestine is a tube. And just like any cylinders from your physics, the fastest flow in any tube is in the center of that tube, right? And so the closer you are to the wall of the tube, the slower the flow of any fluid. And the reason for that is because there's friction between the molecules that constitute the wall and the molecules that are in the solution that are flowing, right? And if you go right on top of the wall, which is represented here, there's actually an unstirred layer. And that unstirred layer means it's just like an overlying layer of aqueous medium. Remember, this is a high magnification. So basically, over here in the lumen, it's well stirred. Okay, this is where the flow from mouth to anus is fastest in the middle. But right here on the very, very top of your intestinal cells, your intestinal absorptive cells, is an unstirred layer. And this is the aqueous medium and this is of course aqueous solution. So if your fat digestion products were not incorporated in micelles, they cannot cross this. So for lipid absorption, this is really the rate limiting step. If you don't have micelles, you are going to defecate your lipid digestion products because the hydrophobic lipid digestion products just do not cross, or very, very cross, or in slow rates, actually go through here by diffusion and then go through here across the lipid bilayer by diffusion. Okay, so it's very difficult for these lipid digestion products to cross the anterior layer. So what do micelles do? Because the micelles are actually can penetrate the anterior layer. Because remember, their surface is hydrophilic. So they bring the fat digestion products close to the lipid bilayer, and because the lipid bilayer is hydrophobic and these fat digestion products are hydrophobic, they can merely diffuse through. So that's really the role of the micelles. And as you can see, the bile acids are therefore trying, without bile acids, first in the emulsification step to increase the efficiency of pancreatic lipase, and then for these bile acids to help form micelles. And micelles, you can think of micelles have buses that bring, or high-speed trains that bring lipid digestion products from the well-mixed luminal contents in the middle of the intestinal lumen right to and very, very close to the membrane. So they're like buses. And so instead of these lipid digestion products walking through here very, very slowly, because they really cannot penetrate here, the aqueous medium right here, they're actually being brought by these micelles onto the surface, very, very close to the surface. The bile acids themselves do not cross, okay, because again, they have a hydrophilic component. So that's really the important role of micelles. And these micelles are very important for the diffusive component of lipid absorption. However, there are some lipid digestion products that are hydrophilic enough that they have difficulties diffusing through the lipid bilayer. So therefore, a major protein that facilitates the diffusive but mediated absorption of hydrophobic/hydrophilic fatty acids through the lipid bilayer is by this FATP transporter, or in short, this is called fatty acid transport protein. So this is very easy to remember. Without micelles, absorption is possible but inefficient. And bile acids, as I mentioned, do not get absorbed together with these lipid digestion products. The bile acids are absorbed in the distal ileum with their own specific transporter, because they need to be recycled once their work is done, and that location where they're reabsorbed is found in the ileum. Okay, so this is your intestinal cell. We now have your fatty acids and 2 monoglycerides in the cytosol. Again, they have a problem because the cytosol is, of course, hydrophilic, right? So they're hydrophobic. So immediately after absorption, they're actually incorporated in the smooth endoplasmic reticulum depicted here. And these smooth endoplasmic reticulum, they're not passive, they just don't sequester these fatty acids that came from lipid digestion. What they actually do is they re-esterify the fatty acids to the 2 monoglycerides, so that they are incorporated and they again become triglycerides, as shown here. So in a way, and I'll give you a big picture in a later slide, that's really quite complicated way of doing it. So you eat, if you had ice cream for lunch, if you had hamburger for lunch, if you had cheese for lunch, the lipids there are triglycerides, most of them, many of them. And then we spend energy into breaking them down in the intestinal lumen. Then we absorb them. Once they are absorbed and enters here, we spend energy again because they are again hydrophobic molecules in a hydrophilic environment. We re-esterify them, and after they are re-esterified to become triglycerides again, then they form lipid droplets in the smooth endoplasmic reticulum. From there, they're transferred to the rough endoplasmic reticulum. What is the job of the rough endoplasmic reticulum? What these organelles do is to coat these droplets with apolipoproteins, as depicted, here. So this is your rough endoplasmic reticulum, and so now these are your lipoproteins that should be wrapping the chylomicrons that are found and exiting via the basolateral membrane of these intestinal cells. So now these lipid droplets are mainly, the surface of this are mainly apolipoproteins and also phospholipids. Remember that the phospholipids, always from your organic chemistry, they have a polar head group and a non-polar tail. Okay, so that's why the lipid droplets, the phospholipids, their hydrophilic components would be on the surface of these lipid droplets. At this stage, these are now called chylomicrons. So chylomicrons are not micelles. Micelles exist in the lumen. Chylomicrons exist, pre-chylomicrons exist in the cytosol. Chylomicrons exist in the bloodstream. And then finally, so we have your chylomicrons here with, you could see the polar head groups of phospholipids being shown right there. And then all your triglycerides and cholesterol esters are right here in the middle, and it's wrapped with a lipoprotein coat. And these chylomicrons cross the basolateral membrane by exocytosis. And once they are in the submucosa, they cannot fit through the basement membrane. And so therefore, they go through the lymph circulation and enter the bloodstream through the thoracic duct. And then that will be brought to the liver for processing. So these are, again, your chylomicrons wrapped in apolipoproteins, and then they are exocytosed. They diffuse through the basement membrane, go into the lymph capillaries, and then enter through the lymph, and then actually join the blood in the thoracic duct, where the lymphatic system and the main circulation of the body, blood circulation, actually meet one another. So this is a big picture of the complicated process of fat digestion and absorption. So you begin with dietary fat. This is your ice cream here in fat globules. Then the fat globules are incorporated and broken down into emulsions, and then the emulsions are acted upon by your enzymes. So your bile makes sure that emulsions are made, then bile and your enzymes digest your lunch into absorbable lipids. Again, these absorbable lipids encounter bile, and bile makes micelles out of these absorbable lipid digestion products. They cross the unstirred layer. You can imagine an unstirred layer here. These are your intestinal cells. This is your intestinal lumen, and this is your blood side with a lacteal here. Okay, so now you cross the unstirred layer. The lipids are now in the cytosol. Well, they're immediately grabbed by fatty acid binding proteins and brought into the smooth endoplasmic reticulum. And there in the smooth endoplasmic reticulum, they are reprocessed into triglycerides again. And then in the rough endoplasmic reticulum, they are wrapped with apolipoproteins, depicted here. And then these chylomicrons are extruded from the basolateral membrane of these epithelial cells by exocytosis, and then they enter the lymph circulation via a lacteal here. And then these, the lymph circulation transports chylomicrons away from the intestine. So compare this, if you actually put lipid digestion and string them together from beginning to end, you have a large number of slides. If you go to carbohydrate digestion and string the digestion and absorption together, you have 3 or 4 slides. If you go to to protein digestion, also again a few number of slides, 4 to 5. But lipid digestion products actually require a lot of involve a lot of processes. And so now here, and I hope you get the big picture, that bile is truly essential for efficient digestion of lipids, followed by efficient absorption of lipids from the intestinal or GI tract lumen into the cytosol, and from the cytosol via chylomicrons into the lymph circulation. Okay, are there any questions about lipid digestion or absorption? Sorry. Okay, so let's now go into the next slide, which, if I can make it work. Oops. Now we have a problem. So we go into electrolyte and water absorption. Recall the fact that you have 7 to 9 liters of fluid secreted by the organ systems in your GI tract, right? So that fluid should actually be, most of that should be reabsorbed, so that at the end of the day, you only have, in normal conditions, between 100 to 200 ml of fluid in your feces. Otherwise, you will die of dehydration, or just drink 10 liters of fluid a day, which is quite difficult to do. So this is your intestinal mucosal layer. This is the food side. This is the blood side. This is your paracellular pathway. And this is the pathway for fluids and electrolytes to go from the lumen into the blood side. One other way that they can go through is via a transcellular pathway going through the apical and basolateral membranes. So fluids and electrolytes are actually going through both routes, okay, depending on what region of the intestine you're in. Now, your intestinal regions differ markedly in paracellular permeability. So your most proximal region, the duodenum, is the most permeable. And then the next one in ranking is jejunum, then ileum, and the least permeable is the large intestine. Here actually paracellular absorption approaches the rates that equal that almost of transcellular absorption through the transcellular pathway. So that, and then the transporters for various ions are more abundant in distal regions. And I'll explain that in a few slides. So this is the duodenum. In the duodenum lumen receives fluid from the stomach. So if you actually ate very salty food, that means there's going to be very hypertonic solution, that you swallowed. If you drank a lot of water with your food, then you have a hypotonic solution probably in your duodenum. And so this is basically what happens. This is the food side, this is the blood side, and this is your intestinal mucosal layer. So the flow, remember in the duodenum, there's a low resistance paracellular pathways. So if this is hypertonic because you ate something really salty or very sweet, very sugary, then fluids will flow from blood side to food side because this is concentrated. Now, if you drank water, then a lot of water, then this becomes hypotonic, and then fluids would go from the food side or luminal side to the blood side. And I will show you what happens when, in there as well. This is occurring again in the duodenum. In the jejunum and ileum, this pathway is now much less permeable than in the duodenum. The contents are isotonic. So therefore, there is not much gradient for passive ion and water transport. And ion transport become more and more dependent on transporters. Remember, ions are high, they're in solution, they're actually charged. And so these are very, very highly hydrophilic. And they don't cross the apical membrane. They don't cross the lipid bilayers. So how are these electrolytes absorbed? So this is your intestinal cell, this is your food side, this is your blood side. So now you have a lot of sodium that is being secreted here from either because you had a lot of salt, or it's coming perhaps from the more proximal regions of your GI tract. So now you have sodium here, and sodium and chloride transport occur by mainly transporters in the jejunum and ileum. So one way, you have learned this already, is SGLT1. SGLT1 is sodium-dependent glucose transporter 1, and it co-transports with glucose a sodium ion. This is a required partnership. So without glucose, sodium cannot be absorbed via this pathway. It can still be absorbed via that pathway. If you have no sodium, then glucose cannot be absorbed. So this is important way of absorbing sodium via co-transport with nutrients. And then remember that some amino acids also are sodium dependent, some amino acid transporters. So this is route number one for sodium absorption. Another route is via this apical sodium hydrogen exchanger, exchanging sodium with while extruding protons. So absorption of sodium, expulsion of protons. And the sodium is then brought from the cytosol to the blood side via sodium potassium ATPase. What about absorption of chloride? Well, we already talked about the chloride bicarbonate exchanger. So in exchange for bicarbonate, chloride is absorbed. This is the transcellular pathway. There's also a paracellular pathway because electrically, your blood side is actually positive compared to your food side, electrically positive. And that attracts a small amount of chloride ions to go through the paracellular pathway as mentioned here. Now the bicarbonate would combine with the proton to make carbonic acid, and then carbonic acid then splits into water and CO2. CO2 is lipid soluble actually, and it just goes through the membrane. For essentially, this is what forms, part of what forms gas in your GI tract. So as you can see here from this depiction, sodium here and chloride are almost always absorbed from the lumen into the cell, excuse me, and from the cell into the blood side. And CO2 is then brought to the bloodstream and expelled in the lungs. So if the contents of the jejunum is isotonic with that of the blood, how can you absorb water? Okay, because you have a semi-permeable bilayer here of epithelial layer, and then you have net absorption of water. But how can that be when one side is isotonic to the other side? And so this is what is called the standing gradient mechanism, explaining how we absorb water. And so this is sort of a summary of what we just previously talked. So this is your paracellular pathway. This is your transcellular pathway. So this is now in the jejunum relatively highly resistant to water flow and ion flow. So you have sodium and chloride, your sodium hydrogen exchanger and your chloride bicarbonate exchanger, bringing in sodium chloride from food side into the cytosol. And then the sodium chloride, the intestinal cells are a lot longer than they are wide. So the surface area along the lateral side is very high compared to the basal side. So what then happens is that the sodium and chloride are transported from the cytosol into the space between intestinal cells. So this process goes on and creates a hypertonic, transient hypertonic environment here. So this is the transient hypertonic environment. So now you have something hypertonic. And because it's hypertonic, water is then attracted to this hypertonic area, and it goes through aquaporins in the apical membrane and aquaporins in the basolateral membrane. Aquaporins are water channels that they go through, and then they actually then dilute the sodium chloride that's found here between the cells. So these are transient hypertonic lateral spaces. So the way, therefore, we absorb water when both sides, the blood side and the food side, are isotonic is by this standing gradient mechanism. So you, by your sodium and chloride transporters, you bring it in, and then via sodium-potassium ATPases, and they are the sodium and chloride pumps here actually in the higher region of this intercellular space, then dump the sodium chloride in the intercellular space, thereby creating a transient hypertonic environment. And so this hypertonic environment attracts water from the food side into the blood side. And so water through aquaporins would then move from the food side via these aquaporins in the apical and basolateral membrane, and then be extruded into the intercellular space. Once the intercellular space is getting full, then hydrostatic pressure builds up, and then water and ions just flow through the basement membrane. So this is how we absorb water and fluids in general from two sides, where one side is isotonic to the other. The luminal side and the blood side are isotonic. A similar process occurs in other regions where water is actually absorbed: ileum, colon, gallbladder. So now let's go into the colon, and it's the least permeable, even less permeable than the ileum. So it's difficult for ions to go through the paracellular pathway. So we know that your colon, your colonic cells, they don't absorb nutrients. There is no SGLT1 here, no amino acid transporters. However, they have similar systems. They have sodium hydrogen exchangers to absorb sodium, and chloride hydrogen exchangers to absorb chloride. They also have two extra transport systems, mechanisms not found in the small intestine. One, they are able to absorb sodium through ENaC channels into the cell. And so these channels are actually very important, and I believe Dr. Rojax next Monday will be discussing this. So, but he will discuss it in the kidney. So here the ENaC is found here, and this is under the regulation of the hormone aldosterone, so that this aldosterone increases the number of ENaC channels when plasma sodium is low. So we release aldosterone when plasma sodium is low, and then we reabsorb then sodium that's found in the that's essentially found in the colonic lumen. The second one that is being absorbed is secretion through potassium channels. And and some books emphasize the fact that these are high conductance channels, or the name is BK. It stands for big potassium channel, going from cytosol to the lumen. And when you have diarrhea, under normal conditions, this doesn't pose to be a threat. However, it can lead to hypokalemia in chronic diarrhea. For those of you or people who are actually have chronic diarrhea, they are in danger of having low potassium in your bloodstream. And you do need to supplement your potassium, supplement it with potassium tablets. Because when there is diarrhea and the flow of fluid through here is fast, then potassium is actually actively secreted by this BK potassium channel. So once inside here, then sodium is reabsorbed. The chloride is brought from cytosol to the blood side via a channel here. And then you still are able to absorb chloride and sodium via these two mechanisms we have already seen from previous slides. Now, none of us have been exempted from having a diarrheal episode. Okay, so what actually happens in infectious diarrhea? So this is diarrhea that's caused by a toxin coming from bad bacteria. And so these here, this map of the United States show you the number of E. coli outbreak in 2018. And the dark blue ones have more outbreaks. And here in New Jersey, we do have a fair number of outbreaks. The kinds of outbreaks came because of contaminated romaine lettuce. You were probably still in undergrad here. Ground beef, there was a recall of ground beef because of E. coli presence. And romaine lettuce, again, similar strain that was detected in romaine lettuce samples that the FDA investigates. So this is actually a frequently fair number of occurrences over the years. And this is this is E. coli in the United States. This is cholera. This is actually a virulent disease, right? You've heard of cholera. And this is the episodes of cholera cases in 2015 in different parts of the world. So, and as you can see, we don't have a lot of cholera here. We are, in the United States and Canada actually is very careful about this potential infections by cholera, because it is a deadly disease. But warm areas like Mexico, these are India, these are now Cambodia, Thailand, this is the Philippines, this is Malaysia, and then Indonesia. These warm countries, this is New Guinea, they actually have outbreaks of cholera. So what happens when you have cholera or E. coli? So this is the food side, this is the blood side, and this is your famous intestinal cell. So you ingested, you were touring Bali, Indonesia, or Phuket, Thailand, trying to enjoy your upcoming summer, and you sampled street food, and unfortunately the street food might contain cholera. Well, the bacteria actually do not enter your body. They secrete toxins in the lumen. These toxins, the cholera toxin has two subunits, alpha and beta, or A and B subunits in different books. The alpha subunit is recognized by a ganglioside GM1 in the apical membrane of your intestinal cells. So GM1 is found there to regulate transporters. It is not there to normally recognize cholera toxin. Just like COVID-19 viruses use ACE2 to enter our bodies, okay, it hijacks a transporter. This toxin also hijacks a component, a regular component of the apical membrane of intestinal cells. So GM1 is recognizes the alpha subunit, the beta subunit, and then the alpha subunit, apologies about that. So the beta subunit is the one that's recognized by GM1. And then once this partnership, this link occurs, the alpha subunit enters the cell. And so what does the alpha subunit do? Well, it binds to the GS proteins, your G proteins from your biochemistry, and activates and stimulates adenylyl cyclase, or AC here, and then produces copious amounts of intracellular cyclic AMP. Well, cyclic AMP is actually a regulator of a chloride channel in the intestinal cell. If there is an enormous amount of cyclic AMP, they actually can cause chloride secretion, because CFTR is a chloride channel. And so cyclic AMP activates permanently the CFTR. The CFTR is actually a channel, and under normal conditions, right here where you're listening to my lectures, this is closed, and it maybe opens every now and then, okay, because of the presence of cyclic AMP. If you have cholera, then cyclic AMP production increases, and the increased cyclic AMP activates CFTR and locks open this CFTR, so that chloride now has a free rein to go from the cytosol to the food side. And when that happens, the food side becomes negative, more negative, and then attracting sodium and water. So these fluids that are flowing out here are then responsible for the deadly diarrhea that occurs in cholera. So under normal conditions, your absorption rates vastly, is much higher than your secretion rates that is here. However, when you have infectious diarrhea because of cholera or E. coli, your secretion, net secretion, will be way over that of your net absorption. So that if actually untreated, almost 3/4 of cholera toxins can die from dehydration and loss of salts within hours after the onset of symptoms. Actually, what happens in severe cholera cases is you just stay in the bathroom. And then when you become weak enough, then you just fall, and then you still are having diarrhea. It's not a very pleasant disease to have. Okay, so how do we treat this? Okay. What we do is we rapidly replace water and salts. This is the most, actually popular way of addressing infectious diarrhea. And how do we do that? So we do what we call the oral rehydration therapy, or ORT. And it takes advantage of the fact that SGLT1, doesn't care whether there is a toxin or not. It's there. And SGLT1, remember, absorbs 1 or more sodiums per glucose absorbed. So when it does that, as I can show you here, for 1 glucose that's absorbed, 1 sodium is absorbed. And then once inside the cytosol, the sodium is absorbed into the bloodstream. So while there is CFTR releasing chloride and sodium also going out through the paracellular pathway, you have this process being activated. So now you have your sodium entering and replacing the lost sodium that is being extruded via diarrhea. So with these solutions, you add potassium, and bicarbonate is to make it less acidic. So what are these oral rehydration therapy? Well, if you are athletic and you guys play tennis, or you jog, or you swim, then a simple way of rehydrating is via Gatorade, for example, that there's glucose and salts there. In fact, if you watch the Super Bowl, there's actually, Pedialyte is the go-to rehydration solution for infants. So Pedialyte has actually now, the company Pedialyte has now made the equivalent Pedialyte for adults to compete against, these more
No, Jube
popular
has them.
brands
I only
like
have one,
Gatorade.
but it's not even a full picture.
So if you have infectious diarrhea and
I'll
it is not
send you
severe,
what I
you
have.
can just treat yourself via oral rehydration therapy. Of course, if it is severe, you would have to go to the hospital so that you can be rehydrated via intravenous solutions. So we rehydrate ourselves via SGLT1, okay? And that's primarily this oral rehydration therapy. So now we go into mineral absorption. And we require minerals for normal metabolism. And I really only have time to describe calcium and iron. So we focus on calcium because a lot of Americans are deficient in calcium. Iron, 1/3 of Americans are deficient in iron. But actually, there is a sex-linked deficiency here. Most of the people affected here are primarily women, especially women of reproductive age and women who are pregnant. Okay, this is really obvious because of their monthly losses of iron. So we discuss calcium and iron. And we actually absorb a lot of calcium. Okay, so the gastric acidity in our stomach liberates calcium from our food, and then this free calcium ion can then be absorbed by a transcellular route in the duodenum or by a paracellular route in the jejunum and ileum. Paracellular just goes through the tight junction. So let's discuss the transcellular route of absorption, okay, in the duodenum. So this is a duodenal cell. This is the food side. This is your cytosol. So this is the events that are happening between in the transport of calcium from food side or lumen side into the cytosol side. Okay, so calcium is hydrophilic, cannot go through the lipid bilayer. So it has to be absorbed by CAT1. Okay, this is very easy to remember. Calcium transporter 1. Many books now increasingly call CAT1 as TRPV6. TRPV6 stands for transient receptor channels. And there is also a calcium channel in the kidney that Dr. Rojas will be discussing. That's TRPV5. So TRPV6 is an important transporter because for a lot of us, we are deficient in calcium. So you know that from your signaling lectures that calcium concentration in your cytosol is actually pretty low, right? Because calcium is involved in signaling, so we keep it low. So our cytosolic processes don't get confused. So calcium is recognized by this calcium channel, and it goes very rapidly down an electrochemical gradient from food side to blood side, from food side to the cytosol. The cytosol is electrically negative compared to the lumen. So there is an enormous electrochemical gradient driving this downhill absorption of calcium via CAT1. Once inside the cytosol, we don't want to be confused about calcium signaling, right? Because calcium, as we even, acetylcholine uses it, etc., as signaling. So it's immediately bound to a calcium binding protein called calbindin. So that's calbindin is calcium binding protein. So we sequester calcium either by binding it with calcium binding protein or sequestering it in vesicles. Calbindin is sometimes called CABP in some books. Okay, now how does calcium get out from the cytosol into the food side, into the blood side? So this is by basolateral membrane. The main route of calcium transport from the cytosol to the blood side is via calcium ATPase. So because calcium is an important mineral and because of the enormous uphill electrochemical gradient that's preventing calcium from going from the cytosol to the blood side, we spend ATP, a lot of ATP, to transport calcium across the basolateral membrane. Calcium can also exit via the sodium-calcium exchanger using the sodium gradient as its method of spending energy. So calcium transport across the basolateral membrane is energetically expensive. A minor component of this calcium transport, the two minor ones, is this exchanger or via vesicles, and which exocytose, and the calcium contents of these vesicles are extruded into the blood side. So how do we ensure that we have enough calcium? So we actually have not only take a lot of calcium in our diets, but also have vitamin D. Okay, so if for one reason or another we don't have calcium in our diet, for one reason we're traveling or wherever we are, then our body compensates by making more TRPV6 and calbindins to try to compensate by the reduced concentration of calcium in our diet. Vitamin D is an excellent regulator of calcium absorption. So this y-axis here is duodenal absorption of calcium, and the x-axis is time. So this is in control humans absorbing vitamin D, absorbing calcium. This is the rate of calcium absorption. And then when you take vitamin D at the same time, you actually double the rate of calcium absorption, because vitamin D stimulates absorption of calcium at all levels: paracellular, apical, cytosol, basolateral. So vitamin D is an important vitamin because of its role in calcium absorption. What happens if you don't have enough? Chronic calcium deficiency in children and in older individuals. You have poorly developed bones and teeth. You can develop rickets, and in the elderly, you could have osteoporosis because of lack of calcium. What about iron? So we need iron for proper red cell function. And most adults require a small amount, 10 milligrams per day. Double that for women of reproductive age, which includes half of you here. Okay, and then for pregnant women, it even triples the normal requirement. So how do we absorb iron? Iron absorption is actually complicated. And if it's absorbed in the small intestine, absorption efficiency tends to be low. Vitamin C improves the absorption of non-heme iron, which I will describe to you in a minute. And then for those of you who are vegetarians, there are actually phytates found in legumes, grains, and soybeans, which inhibit non-heme iron absorption. So vegetarians are at greater risk of being iron deficient. And in fact, my own daughter is a vegetarian almost for over a decade, and she's now pregnant, and her OBGYN is supplementing her diet like crazy with iron tablets. So iron tablets are non-heme iron. Okay, heme iron is, as the name implies, comes from the breakdown of hemoglobin, and therefore from red meat, myoglobin in red meat. So this rectangle here represents an intestinal cell. This is the apical membrane, food side, cytosol, blood side. Okay. There's two kinds of iron. Elemental iron that's found in non-heme iron that's found in your diet and in your tablets. And they normally occur in trivalent form. So that's your iron here in trivalent form. However, our body, and especially the intestinal cell, doesn't like trivalent iron. It's too reactive. So it reduces trivalent iron, while this iron reductase that's found in the apical membrane. And so iron reductase is reduced to divalent iron. And divalent iron is absorbed by DMT1 in a proton-dependent process. So divalent iron enters via DMT1. The name is divalent metal ion transporter or divalent cation transporter. So easy to remember, and books can call them by either of these names. So now we have divalent iron in the cytosol. What about the heme iron? So heme is from red meat, and it's released from these other proteins by proteolytic reactions. So there is a heme transporter in the apical membrane. So this heme transporter basically absorbs heme intact from the intestinal lumen through the apical bilayer and into the cytosol. And in the cytosol, you have a heme oxidase, which separates the iron, divalent iron, from the heme proteins. Okay, so this is what happens. This is from pathway from heme heme oxidase. So now we have divalent iron from this pathway, the heme pathway, and the non-heme pathway. Now, what do we do to these iron? Okay, so under normal conditions, it is bound to iron binding proteins. Some books call it mobilferin, okay, in the cytosol. So iron has liberated iron here from these two pathways have two fates. One binding to mobilferin, which is a reversible kind of binding, and irreversible binding to one that is called ferritin. So now how do we do this? So this is your mobilferin pathway. Okay, so you have your divalent iron. So one pathway is this one. Remember, binding to divalent iron is divalent iron to ferritin is irreversible. So if your iron status is high, so for example, you feasted on meat this weekend because you went home, you were salivating like crazy because your mom or your dad was cooking your favorite steak, your very expensive steak nowadays. So you have lots of iron. And so therefore, if you don't need that much iron, the body encourages this dietary iron to be bound to ferritin, so that less iron goes through this pathway. When the intestinal cell dies, okay, then it's extruded into the lumen. The excess iron that is bound to ferritin is then defecated. So if you actually eat tons of iron, right, your stool gets black because that's really the iron that's bound to ferritin. This is when you have excess iron. Now let's say for women here would be a paramount example. Shortly after you have, let's say, an unusually heavy menstruation period. Okay, so now your body has little iron. Obviously, it will not irreversibly bind the iron through this ferritin. It will favor this pathway. And so less iron goes here and more iron goes this way. And therefore, it's recognized by this FPN, or the name is FPN is sufficient, or ferroportin. And ferroportin is then takes this divalent iron and brings it into the extracellular fluid. Now, our body actually measures, likes trivalent iron as its currency. So it will not accept divalent iron. Remember, we converted trivalent iron found in your food to divalent iron because trivalent iron is too reactive, okay, in the cytosol. And instead of wreaking havoc in this part, okay, we deal with it in divalent terms. And then, but the body doesn't like divalent iron. So we have another protein called HEPH, or hephaestin. Okay, yeah, this is the HEPH, and that's the name, and you will find this in books or Wikipedia. And then, so more iron in this pathway is sent through here, and then this pathway then is favored, and then the trivalent iron is bound to a protein in the blood called TF, or transferrin, as it's called here. Transferrin binds only trivalent iron. So you can see that iron absorption is actually rather complicated, right? Um, and but it's, if you follow the logic, and since I lecture very well, then you could obviously understand what's going on. Okay, vitamin absorption. Okay, you have a large number of vitamins, and you know, I know I take extra vitamins, vitamin B, primarily a day, and I know this is very popular supplement in everyday lives of many Americans. So we have this list of vitamins, and I call your attention primarily into three. Okay, there's very popular ones. Vitamin C. A lot of people take this to minimize cold. A lot of people take vitamin C to deal with COVID and so on. For whatever reason, ascorbic acid is hydrophilic, and it cannot cross the apical lipid membrane by itself. So it has its own transporter. It's a sodium-dependent vitamin C transporter. Sodium-dependent vitamin C transporter. Now, sometimes, why do you need to supplement yourselves, especially if you are recovering from an illness, if you're pregnant, or if you're going to the Olympics to, for a really stiff competition? Then you take extra vitamins, and a lot of Americans are actually deficient in pyridoxine or vitamin B6. This needs special mention because you need to be aware of the fact that vitamin B6 is only absorbed by diffusion. So it's a very slow process. Finally, we have vitamin B12, and it's absorbed only in the distal ileum, just like our bile acids, and it is by receptor-mediated endocytosis. And it's here that if you have a deficiency, remember that the parietal cell secretes intrinsic factor, and I think this was also in your quiz today. And let's say, for example, you had bariatric surgery, or people with bariatric surgery. They can become deficient in cobalamin or vitamin B12 because they no longer have intrinsic factors being produced by parietal cells. And remember, in our stomach lectures, the parietal cell secretes intrinsic factor, which is the only secretion in the stomach that's essential for life. So how do you deal with deficiencies? You, of course, have supplements in vitamins, or if you have reduced transport because for one reason or another, you had ileum resection, or people who have ileum resection, you've had of relatives with bariatric surgery, then these are secondary deficiencies, and you address that by supplementing them, noting which, if you know the basics of vitamin absorption, then you realize that these are the three vitamins, the two vitamins that are likely to become deficient. And of course, you can have genetic defects. So vitamins, if you actually look at them, their structure in Wikipedia, they tend to be hydrophilic and very large. And other than pyridoxine, they cannot diffuse through the lipid membrane. So they need transporters. And other than these three, you don't have to know the names of these transporters. Unless, of course, you get accepted to medical school, and then you face that reality when I give this lecture again in much more detail. But I hope, of course, for your sake, that I will see you there, right? That's why you study. Okay, so that's okay. So we need the parietal cell secretion of intrinsic factor so we can absorb cobalamin or vitamin B12. So there are now two remaining sections. We will talk about motility of the GI tract. All this food, if you eat food and then they go to your stomach and then it doesn't go anywhere, then you have a problem. Okay, so that's why we have motility. Smooth muscle cells are very important because they act as your conveyor belts. Okay, so just like when you make cars or whatever products you make, you go from one part of the, they make parts and all those parts need to be put together and so they need to be shipped. So muscle cells act as a conveyor belt and they have really two major tasks: moving contents in the proper direction and appropriate speed. Too fast and you have diarrhea. Too slow and you have constipation. You can't win here. You have to do it the right way. Also, these smooth muscles mix food. Okay, they're also responsible. So, what actually happens with smooth muscle cells? Okay, the smooth muscle cells, their resting membrane potential is a misnomer because the membrane potential actually changes with time. There are oscillations in membrane potential, and that is called the basic electrical rhythm or slow waves. If you read GI physiology in any textbook, and it's initiated by the interstitial cells of Kegel, which some of you, if you have histology, will have already met. Okay, just to introduce you to this, so these are the slow waves that I was talking about, changes in membrane potential. And these are, we can talk about this better in the next slide. Okay, so now this is actually your electrical threshold, the short dashed lines. This is the threshold for contraction of that smooth muscle. So above the electrical threshold, there are action potentials. Below the electrical threshold, there are no action potentials, as you can see that. So let's examine, and then this is your smooth muscle contraction, and these are your slow waves. Scenario number one, there is a slow wave, but doesn't cross the electrical threshold or the threshold for contraction. So no contraction happens. Scenario number two, now, it crosses the threshold for contraction and therefore you have a small contraction here. Doesn't cross the electrical threshold. Scenario number three, it crosses both thresholds. Now you have a larger contraction, more pronounced one. But between this one and this one, there are more action potentials here and here. So what happens in number four? When you have more action potentials, the more action potentials you have on top of a slow wave, the greater your contraction. And so understanding this very simple basics actually will help you understand what's going on with motility of the GI tract. And then right now, you have a flaccid tone, but it's not zero. Okay, you're the smooth muscle right now that you're listening to my lectures is fine. Okay, it's maybe even if you don't cross the thresholds, your slow waves don't cross the threshold for contraction. It's the tension is actually in the smooth muscles is not zero. And it's when there is no action potential, what you have is termed tone in various textbooks. Now, each part of the GI tract has a characteristic slow wave. The colon here is the stomach here. This is your stomach. This is your time, and these are your slow waves with action potentials depicted here if it crosses the electrical threshold. So it's about 3 per minute. In the duodenum, it's 11 to 13 waves per minute. Okay, so you could see that. So this is about 1 minute, and if you count the waves, it's 11 to 13. If you go more distally, you have then less waves per minute. And in the colon, you also have slow waves, but you have about 6 slow waves per minute. So what actually happens is if you have, although these slow waves do not determine the fact that the smooth muscles contract, they determine the frequency of contractions, because contractions really occur only on top of the slow waves. And the frequency of the smooth muscle contraction can be modulated. And this specific pattern of slow waves occurs during and shortly after meals, as the behavior of this smooth muscle contractility when you are sleeping, for example, is different. Okay, so here is a graph. This represents your membrane potential. This is time. And these are your slow waves in a smooth muscle wave. So, okay, so that's what's happening. And then you release ACH, acetylcholine, on those smooth muscles. Well, what it does is it depolarizes the membrane potential, so that in this case, it goes the resting membrane potential. The trough of the wave is -50. Here it's about -42 or about 40. Okay, so when you depolarize the resting membrane potential, effectively what you're doing is you're moving the goalposts closer, right? So it's like, if you're kicking a field goal, then instead of the usual 25 yards after a touchdown, it's going to be 10 yards. So it's easier to make an action potential. So and this is really what happens when you put acetylcholine on top of your smooth muscles. You have stronger and stronger contractions. Then what happens when you have sympathetic release, VIP? Remember what happens with your VIP? It's a relaxing signal, right? You always have to go back. That's because GI is very highly integrative. So effectively, and I'm showing you here the cellular mechanism underlying the effect of VIP. Okay, the VIP hyperpolarizes the membrane potential. So you have slow waves. And so therefore, the ability of those smooth muscle cells exposed to norepinephrine or VIP or nitric oxide diminishes because you're moving the goalposts away, right? So that's why if you're, for example, if you really need to go to the bathroom, and you just imagine that you're about to take GI Physiology unit exam and you become extremely nervous, release a lot of norepinephrine because you know that the exam could be difficult if you don't study. Then you release norepinephrine and you don't have to go into the bathroom anymore. So thus the urge to go to the restroom disappears when you're scared, or actually simply when you're exercising. So all of us have had diarrhea, hopefully not infectious diarrhea. So OTC is over-the-counter drug like loperamide, which is Imodium, right? we've had at one time or the other in our lives have had Imodium. So what is loperamide? It's an opioid receptor agonist. Okay, so and it's an opioid. So it's actually loperamide. Imodium is actually an opioid, and it's metabolized in the intestine. But it is metabolized in the intestinal wall and have minimal effects on the central nervous system. The molecular mechanism underlying the antidiarrheal effect of loperamide is the fact that opioid receptors inhibit the release of acetylcholine. In other words, it is an inhibitor. It activates the inhibitor of ACH release. Now, morphine, okay, for those of you who have undergone surgery, serious surgery, so that you receive morphine, and then that painkiller, morphine, inhibits ACH release. And it has exactly the same as loperamide, except this is highly addictive. And if you know, and for one reason or another, if you go into psychiatry and you deal with opioid dependency, one of the side effects, people can tell, people always, addicts always will never accept that they are addicted to anything. And so you ask very simply how often they go to the bathroom. And if they're frequently constipated, it is actually a sign. It's not, of course, equates to addiction, but it helps in the diagnosis, right? Because of this. So, because drug addicts, if you really are on very high on it, you don't have to go to the bathroom. You just enjoy life. You think, yeah. So what actually happens here is that, for example, this y-axis here is transit time, and x-axis is just, this is loperamide. What happens to food when you take loperamide or take a vehicle or just saline? Then the rate of absorption decreases by half when you have loperamide, which then allows food substances to stay in the intestine, allowing for more fluids to be absorbed out of the chyme. And antidiarrheal drugs inhibit peristalsis. So this is really the GI tract, that we are associated organs, and they are actually sequestered into various compartments. And the sphincters divide the gut into intestinal segments. So the upper separates the oral cavity from the esophagus, the lower esophageal, the esophagus from the stomach, pyloric, the stomach from the duodenum, and so on and so forth. All of these are in play, and we're going to be mentioning virtually all of them in this next several slides. Okay. Mouth and esophagus movements. What happens when you swallow? Okay, so this is your meal for lunch, and let's just say that this is lamb biryani for those of you who are fans of Indian cuisine. Okay, so this is your lamb biryani. This is your mouth, this is your oral cavity, this is your pharynx region, and this is the pharyngeal muscle represented here by blue. The yellow is your esophageal inlet, and this is the muscle, cricopharyngeus muscle, that closes this inlet tightly against the cricoid cartilage shown here. So this is closed all of the time, ladies and gentlemen. But the esophagus is really relaxed at this time. So you decide to swallow your lamb biryani. And so this is now your hard palate, the roof of your mouth, your soft palate, the back of your mouth, your tongue, the lamb biryani, epiglottis, trachea, esophagus. You swallow, and when you swallow, this is what happens. The soft palate is pushed back. If you want to experiment on your little brother, you can feed him and ask him to go upside down and swallow something, and swallowing continues, basically. Okay, actually don't do that. Just so, and then this bolus of food, even if you're upside down, actually is highly regulated, and it goes into the pharynx. When that happens, the food stimulates the tactile receptors in your pharynx, and this initiates a second stage of swallowing. So here, this is your upper esophageal sphincter. It opens, it relaxes for 1 second because it's normally closed, remember? And then it closes here for another second. And then it goes to its contracted baseline. So in this involuntary phase, the respiration, you don't breathe in. Otherwise, your food goes into your trachea and you choke, of course. Okay, so the trachea is covered by your epiglottis, and food goes into the esophagus. Okay, so this is a complicated graph, and the rest are actually relatively easy. So this is your pharyngeal area here. We just talked about the involuntary phase. This is your upper esophageal sphincter. This is your lower esophageal sphincter, and this is your stomach. And this is the y-axis here are pressures. Okay, so your upper esophageal sphincter is normally closed. I just mentioned that. Always closed. And then when you eat your lamb biryani, I mentioned it relaxes for 1 second, and then it contracts forcefully for another second, and it goes back to its contracted baseline. So that's what's going on right there. Then once it contracts, it triggers a primary peristalsis, shown here. And the primary peristalsis is a moving wave of contraction that goes from the upper to the lower esophageal area. And you could see this wave going down, progressing from proximal to distal esophagus. When your UES contracts, it signals the LES to open. This is so that, if you drink fluid with your lamb biryani, the fluids arrive earlier and they can enter the intestine very quickly. And then the primary peristalsis goes down, and then the primary peristalsis, once it arrives in the LES, it contracts it for 1 second again, or a couple of seconds, and goes back to its normally contracted tone. So the esophageal body, ladies and gentlemen, is flaccid. The sphincters, they are normally contracted, as you can see. And the moment it arrives, the primary peristalsis arrives, it tells the LES to contract. And if the primary, let's say you swallowed something and it's stuck in your esophagus. How many of you have had that experience? Right? So that's, then what the problem with your esophagus is that it doesn't like to be distended. Anything that's inside, it dislikes it a lot. So if your primary peristalsis is insufficient to push the food all the way down and it's stuck in your esophagus, then it initiates a secondary peristalsis. It's controlled locally. The bolus of food, if in this expanded version, behind it, the smooth muscles behind it contract, and the smooth muscles in front of it, distal away from the mouth, relaxes. And the reason secondary peristalsis is painful is that it persists for so long as there is food lodged in your esophagus. And of course, the way you get rid of this is to drink fluids. And hopefully that fluid is sufficient to push the bolus, the stuck bolus of food down. So that's why you have secondary peristalsis. So food now enters into your stomach. This is your proximal stomach or fundus, as shown there. And this is your cardiac region. This is the antral region. And this is your pacemaker region, where the contractions go from here distally. And so this is your esophageal, this is your esophagus, stomach, duodenum. So the upper region of the stomach doesn't typically contract. This is in the cardiac upper fundic region. However, below the pacemaker, there is a slow wave, and of course, it's 3 per minute, right? This is upper mid, lower mid, pyloric region. This is now in the pyloric area, and this is in your duodenum, which is contracting at 11 to 13 per minute. Okay, you have the, sorry, not contracting, but the slow waves occur at, because these are membrane potentials. Membrane potentials are a slow wave frequency of 11 to 13. So these are your pacemakers from your pacemaker. So this, it's propagated distally, these slow waves. And as you can see that, and that's your duodenum. And essentially, this is what happens. If the pyloric sphincter is closed, then you have actually a mechanical digestion that's going on. And as you can see, there is, in this GIF, it's not, but you could see a tiny squirt of that's going through the pyloric sphincter. Okay, this is actually what happens as well. You don't want to flood the duodenum. The caliber of, the caliber, I mean, it's like, it's big, right? The radius of the stomach is huge compared to the duodenum. So, only little squirts. And remember, this is highly acidic, especially towards the end of a meal. And you don't want to have duodenal ulcers. If you drink, Gatorade and water, essentially anything isotonic, the y-axis here is hours, the x-axis is percent emptying. Okay. Now, when you take exam, and I know some of you get rattled, make sure that you read the y-axis, because it can also mean percent filling. So then it goes this way, right? The curve goes the other way. So you just need to be careful. Okay, I mean, not in my exams. I'm not gonna trick you that way. Okay, it's the understanding of the course. But if you take other exams, in whatever, you just need to remember to read the y-axis. So, Pedialyte, isotonic salines are essentially, they go quickly through the stomach. And if you eat something salty at the same time, it delays gastric emptying. And if you have something really acidic, sour, you put a lot of vinegar in your foods, it slows it down. And if you have really fatty foods, then it slows the whole thing down. And you know that this is your liver stroganoff. Okay, so liver stroganoff is a European dish, and basically what it has a lot of fat, as the name implies, and therefore it slows the whole thing down, because lipid digestion and absorption, ladies and gentlemen, is complicated, right? Okay, so, and then if you eat a lot of vegetables, this one is from a volunteer. If represented by plastic beads, or you can just imagine a very highly, you have a lot of fiber in your diet. It's the most potent reducer of delaying factor in gastric emptying. That's why for those of you in a diet, you eat your salads first, because it fills up your stomach lumen first, and then you don't have to eat as much. If you gobble up your beef stroganoff first, then you still have it's not as good as fiber, but you do slow things down as well. Okay, so now we're in the small intestine. So peristalsis is really represented. Okay, it's coordinated. The proximal region contracts and the distal region relaxes. And it moves, and so it pushes the food down. Basically, that's the task of peristalsis, and really there's nothing complicated about that. Okay. And overlapping with peristaltic movements are, so of course, if you take loperamide, it would inhibit peristalsis. And if you have infectious diarrhea, it would stimulate peristalsis because of the volume. And there's also laxatives. Now, if you have segmentation, looks like this. It just mixes the food in. Okay, so it's an overlapping. Okay, so the contents of the digestive tract is basically what do they do? What is the purpose of this segmentation? Well, it reduces the unstirred layer, and it makes your chemical digestion more efficient. And then this is now in the large intestine, which has very low motility. And the frequency there, as you know, is very slow. That's frequency of slow waves. And this maximizes the time for optimal absorption of water and electrolytes, because we don't have a nutrient transporter in the large intestine. And so these are your large intestine, ascending, transverse, descending, sigmoidal. So then, once you have, this is a barium enema, probably, and it takes we defecate, normal people, and because many students ask me this, if you go to the bathroom, once every 2 days to twice a day, that's normal. Okay, you don't go take over-the-counter constipations, anti-constipation, if you're going to the bathroom, once every 2 days. It does happen. You would like it daily, of course. The most normal, it's like a sigmoidal curve, right? So, sorry, it's like a bell curve. The most normal is the one in the middle. It's one defecation reflex per day, and on the edges you have twice per day, and and once every 2 days. It takes only 3 hours. So your lunch, ladies and gentlemen, are already most likely in your large intestine. And there it will languish. Where? Because you want to absorb as much fluids as possible. Again, it varies a lot among individuals. So there are 2 types of movements in the colon, and this is in the colon, it's sometimes called Book's segmentation, which is the same name as in the small intestine. Some books would call these segmentation movements in the colon as hostrations, because this is like an X-ray of a patient with a barium enema, and this is how your colon contracts. Look how powerfully the contraction actually occurs. I mean, this is really small diameter. This is really what actually happens. on on every day, every moment in normal people. And then we have mass movements. So it's a form of peristalsis, and it's essentially what you can think of as a summary of peristaltic waves. Colon also has regular peristalsis, but it's not really the primary propulsive movement. Mass movement occurs 1 to 3 times a day. It doesn't mean that you are going to have a defecation reflex. It just means that things are being pushed all the way back, okay, distally. And it's mediated by acetylcholine. So here, this is the top is a change in membrane potential, and this is your contractions. So this is normally going on. Okay, this is about 6 per minute. This is a colon in vivo experiment or ex vivo experiment, an isolated colon, and then you add acetylcholine right here. So then you have action potentials going on top of that. And now when there's a lot of action potentials, you now have a lot of contractions going on. And the more action potentials, or the longer they are, the greater the contractions. So what's going on during a mass movement is really a ton of ACH that actually go into your colon smooth muscles. And when you wash acetylcholine away, things go to a normal slow waves and no muscular contraction here. So this is your defecation reflex. This is a graph of that mercury pressure, change in pressure. This is your rectum. This is your external anal sphincter, your internal anal sphincter. So you have a mass movement. And in that mass movement, then your rectum fills up. And when your rectum fills up, as depicted here, immediately you have here a reflexive relaxation of the internal anal sphincter, shown here. So once your rectum fills up with fecal material, your internal anal sphincter relaxes. Luckily for you, your external anal sphincter, which is under your control, because remember, the external anal sphincter is entirely striated and innervated by somatic nerves. You reflexively make sure that you are, socially behaving well, and you prevent the contents of your rectum to come out, spilling out in an area that is not appropriate. And so you close your external anal sphincter until such time when you are able to do so and defecate in an area where you can do so without embarrassing yourself. So that brings us essentially to the functions of this smooth muscle. And in the very last portion, and just a few slides, we are going to talk about gut microbiota. So, I don't know how many of you have had this type of lecture, but this is a introduction of a few slides on the human microbiome. We have about 23,000 genes in our body, and the bacteria that actually live in our body along with us have 1 million plus genes. So most of the genes that we carry around belong to the gut microbiome. And in fact, we have most of the microbiome that we have actually are found in the GI tract. And they weigh about, these microbes weigh about 2 kilos or about 4 pounds. So as I mentioned in my class, if you go on a date and want to impress your date about your weight, you can deduct 4 pounds without telling anybody, and you're telling the truth, right? Otherwise, you'll be forced to explain gut microbiome over dinner, which is not a pleasant date topic. Okay, more so about the gut microbiome. So we are not alone. So this is a drawing of colorful drawing, a depiction of your GI tract from your stomach to your rectum. And the representative bacterial genera are found here, some of it expressed in terms of families. And this is the population density. So in the small intestine or in the large intestine, mostly, and sometimes in the ileum, depending on the bacterial flora that we have, we can already have, this is per ml, okay? So it's not the entire lumen. We're talking about per ml here. You have trillions of bacteria per ml. No, sorry, billions. Okay, so I'm losing my exponentials here. So you have billions here. And then eventually in the distal colon, you actually can have trillions of bacteria per ml. In fact, we defecate, there's a lot of living and dying of bacteria. Okay, bacteria, they have lipids too in their membranes. So they don't actually like bile acids, because bile acids can actually, they actually have special enzyme to deal with bile acids, because they don't like bile acids. They live with the bile acids. And some very good bacteria, for example, for those of you who take in probiotics, which will be a later topic in this lecture, the probiotics, many of them are resistant to bile acids. And so this is the composition of your gut microbiota in over time, over our lifetime. And this is the 4 major phyla of bacteria. And you need to know this: Firmicutes, Bacteroidetes, Actinobacteria, Proteobacteria. Fatty acid binding protein. Okay, that would make it easy for you. Okay, so theoretically, unborn babies don't have anything in their gut microbiota, although this is now challenged. Babies that are born vaginally tend to have more than those by C-section. And it does impact their development, according to some of these papers. Now, breastfeeding, so don't worry about this, is different kinds of sequencing, okay? This is one method, another method of sequencing, and you don't have to just worry about these changes. You could see that there's a small change in the composition of the gut microbiota compared breastfeeding with formula feeding. One of the biggest transitions occur when babies transition from being milk-fed to solid food, and you could see that dramatic change. Then you have toddlers, and there really isn't that much change, okay? Toddlers are just bigger babies. However, if you have, if they're malnourished, or if you treat them with antibiotics, you do have remarkable changes in gut microbiota. Chronic conditions like obesity remarkably affect gut microbiota as well. And aging, and is related to slower or disrupted motility, okay? They also have a different kind of gut microbiota composition. And here I illustrate to you that each of us harbors a unique population of gut microbiota. And this is something that you should actually know, because gut microbiota, your siblings and you probably share gut microbes more regularly than your peers. And this is one subject, and these are so the composition of the gut microbiota depends on the thickness of this one. Is time of day. Subject A was paid to volunteer his or her feces for analysis. Okay, that's really a good type of living. Subject B also was paid an x-axis here to analyze her or his feces as every day as a function of time here. Okay, so what's going on? So as you can see, principle number one, and this was done in the Northwest. These two do not know each other, of course. These are anonymous donors. But as you can see, there's a remarkable difference. Okay, this person has more bacteroidetes than this person. And this person has more firmicutes than this person. Okay, subject A actually had a job and went to travel in Southeast Asia. And being a young person, decided to try street food there. And lo and behold, then you have infectious diarrhea shown here. And that's proteobacteria shown there. This occurred twice, from day 71 to day 122. Here, sorry, this is the entire episode from 71 to 122, but the diarrhea occurred from day 80 to day 85, shown here as peaks, and day 104 to 113. So there's two episodes of diarrhea. That food must be good because you go there, you had to experience it again to have another episode of diarrhea. But as you can see here, what I'm just trying to allude to is that the salmonella was detected here, and it's represented by it belongs to the proteobacteria phylum, and that's really the expansion here. This is mainly salmonella. That's what's going on here. Subject B, even if there was no travel involved, may have gone or may have undercooked certain meals, or went to a restaurant with something not good in that, and you could actually see that in this subject B had food poisoning as well, again, proteobacteria again, and as you can see, immediately the diversity of gut microbes reduces. It's characteristic by that. So in other words, the density of gut microbiota actually changes as you have these bad bacteria occupy your gut microbes. Both subjects did not take antibiotics. So normally there are proteobacteria that are found in low levels, but actually, they're actually not found under normal conditions. So when you have situations like this, then your gut microbiota becomes dysbiotic, is the term. And when you have bad microbes inhabiting your gut. So how do you go from an abnormal gut flora to a normal gut flora? Okay, most people just take probiotics here, so you can have, or prebiotics is really food for growth for good bacteria. probiotics are microbes that are claimed to provide health benefits when consumed. And you now, gut microbes are now so popular that almost all, I mean, you go to any almost, any food item that's canned or in fluid, oh, probiotic is, oh, probiotic. Didn't you realize that from the time you were in grade school to now? The manufacturers put probiotic, and immediately they increase the price by 20 cents. It's really nothing, you just add bacteria there and that's it. And then you could also have fecal microbiota transplantation. Okay, so for example, you had a serious C. difficile infection, and this happened, to people a lot in 2013 in the U.S. And it was so bad that antibiotics no longer work. And so the FDA approved, just like they're approving vaccines, fecal microbiota transplantation. What is that? So actually, fecal microbiota transplantation is an FDA-approved process of having a dysbiotic sick person, especially ones confirmed with C. difficile infections. And C. difficile is a bad bacteria under weakened conditions. Okay, so fecal microbiota transplantation is either you introduce the feces of a healthy person into the colon of the sick person, or you package the fecal material in a palatable form, maybe a sundae, maybe with a little bit of fecal flora in there, and give it to the sick person. And I'm not joking. Actually, this is what it depends, because sometimes colonic transplantation don't work. And now they can dehydrate this fecal microbiota from healthy people and put them into capsules, and then you take the capsules. Anything for those of you who have known, C. difficile is actually a very difficult. You do need to address this quickly. And if it's already resistant to antibiotics, then this was the last resort in this major infectious episode in 2013. So that's about it. That's the last. And thank you very much for listening to my lectures. I do work on probiotics and gut microbiota. And so I know some of you have already approached me to learn more about gut microbiota, and I am looking for student lab assistants if you're interested. And a lot of, and most of the time they do thesis work on this one. So thank you, and I need to stop the recording. And good luck in your unit, GI unit, actually your second final, okay, your second midterm. Okay, take care. And if you have any questions, you could, shoot me an email, or I will deal with it. If there's a large number, we can have a quick review session. Okay, thank you so very much again, and all the very best to you in your careers, whatever your plan is. Thank you for, I appreciate you guys coming to me, because I cannot imagine myself, giving a lecture to to an empty room.